Good morning, students. In this lecture, we'll try to cover the piezoelectric and ferroelectric materials and their applications. Okay, so before starting this, we'll recall the crystallography, right? So as we know, there exists 32 types of point groups in 3 dimension. So those 32 types of point groups are classified or categorized into different types based on their symmetry. Okay, so out of these 32 types of point groups or crystal symmetries, 11 exhibit centrosymmetric nature. Okay, 20 exhibits non-centrosymmetric nature. Okay, so based on the situation, out of these 32, one point group exhibit both the centrosymmetric nature as well as non-centrosymmetric nature. Okay, now in this we will focus on this non-centrosymmetric crystals. Okay, so those non-centrosymmetric crystals are also called piezoelectric crystals or piezoelectrics. Okay, so the crystal symmetries which are having or which are exhibiting this non-centrosymmetric nature are also called piezo or piezoelectric materials, or piezoelectric crystals are simply piezoelectrics. Okay, out of these 20, the 10 point groups or 10 crystal symmetries exhibit a special nature called unique polar axis. Those piezoelectric materials which are having this unique polar axis are also called pyroelectric materials or pyroelectrics. Remaining 10 point groups doesn't have this unique polar axis. They are also called non-pyroelectric materials. Out of these 10, the few pyroelectric materials exhibits a special property called hysteresis or spontaneous polarization. Those pyroelectric materials or pyroelectrics which are exhibiting this hysteresis or spontaneous polarization behavior are also called ferroelectric materials or ferroelectrics. Those piezoelectrics, pyroelectrics which doesn't exhibit this hysteresis or spontaneous polarization are also called non-ferroelectric materials. Okay, from this we can say all ferroelectric materials are pyroelectrics and all these pyroelectric materials are piezoelectrics or piezoelectrics, but the converse is not true, because the few piezoelectric material doesn't have this unique polar axis and few pyroelectric material doesn't exhibit this hysteresis or spontaneous polarization behavior. Okay, so now we'll try to cover the basics related to these piezo as well as ferroelectric materials. Okay, first we'll focus on these piezoelectric materials. Okay, so in Greek, piezo, the word piezo means pressure. So we can say the piezoelectricity is nothing but the pressure electricity. Okay, certain non-centrosymmetric crystals such as Rochelle salt, barium titanate, potassium niobate, lead zirconate titanate, lead titanate, etc. exhibits this non-centrosymmetric behavior. Okay, so in this case, in these non-centrosymmetric crystals, in the year 1880, Curie brothers observed a special feature, that is piezoelectricity. Now we'll try to define what is piezoelectricity. Okay, so when you apply pressure on the two sides of the non-centrosymmetric crystal such as rochelle salt or barium titanate, quartz or calcite, whatever. Okay, when you apply pressure on two faces of the non-centrosymmetric crystal, we can observe or the charge carriers are developed on other faces of the or other two sides of the crystal. So this is the definition of piezoelectric effect. Okay, so when you apply pressure or when you squeeze, when you twist the non-centrosymmetric crystal, so we can observe the development of charge carriers or development of charges on the other two faces of the crystal, or the electricity is induced on other two faces of the crystal. So the process of inducing this electric field by the application of external pressure or squeezing or twisting is also called piezoelectric effect. Okay, the converse of this effect is also found to be true. Means instead of applying pressure, when the piezoelectric crystal is subjected to the external electric field, we can observe the change in dimension on other two faces of the crystal. For example, if we apply the electric field, let us consider the dimension of this crystal is increased. When you change the polarity of the applied electric field, okay, so the change in dimension is also reversed. Okay, so this effect is also called inverse piezoelectric effect. Okay, so when you apply the electric field to a non-centrosymmetric crystal, the change in dimensions of the crystal takes place. Okay, so the process of changing dimension in the non-centrosymmetric crystal by the application of external electric field is also called inverse piezoelectric effect. Okay, so instead of applying this DC electric field when the dielectric material or when this non-centrosymmetric crystal is subjected to the AC field, okay, so what happens during first half of the crystal? Let us consider the dimension of the crystal is increased, whereas during the second half of the cycle, what happens? The dimension decreases. If you continuously apply the field, what happens? The dimension of the crystal gets changed. For example, increases, decreases, okay, so finally the atom sets into the vibration. If you apply the AC field to a non-centrosymmetric crystal, what happens? So it sets into the vibration and it produces the vibrational waves, which are nothing but the sound waves. Okay, so the inverse piezoelectric effect is used to produce the sound waves, especially ultrasonic waves. Okay, so this is about piezoelectric effect as well as inverse piezoelectric effect. Okay, so before applying the electric field or before applying the pressure to this non-centrosymmetric crystal, all the charges inside the material is balanced. That is the reason why the net polarization is 0. But when you apply the pressure, the disturbance in the balance takes place, balancing of the charge carriers takes place. So as a result, what happens? The field is produced or the dipoles are induced. Okay, so the induced polarization under the influence of external electric field, under the influence of external pressure is equals to D into sigma. Okay, where D is also called piezoelectric coefficient. Piezoelectric coefficient. For different materials, the value of D may be varies. Okay, so if you see the cross-sectional view of a piezoelectric crystal, okay, so let us take a quartz. Okay, so it looks like hexagon. the two pyramids are attached both top and bottom of this hexagon. Okay, see, the line joining this longest portion of this natural crystal is also called optic axis. This is also called Z axis. Okay, see, the line joining the two corners of this hexagon is also called X axis or electric axis. Similarly, the line joining the midpoints of these opposite faces of the hexagon is also called Y axis is also called mechanical axis. Okay, if you take a piece of this piezoelectric crystal, if you cut this crystal perpendicular to the x-axis, as well as parallel to the y-axis, those are also called X-cut crystals, which are used to produce longitudinal waves. Okay, similarly, if a piece of the piezoelectric crystal is cut perpendicular to the y-axis or parallel to the x-axis, those are also called Y-cut crystals. Those are used to produce transverse waves. Okay, so these are different types of the crystals, piezoelectric crystals, which is used to produce different types of sound waves, okay, or mechanical waves, longitudinal as well as transverse waves. Okay, so the phenomena of piezoelectricity was first discovered by Curie brothers in the year 1880. They observed this piezoelectric phenomenon in non-centrosymmetric crystals such as quartz, calcite, Rochelli salt, okay, barium titanate, lead titanate, etc. Okay, first they observed this in Rochelli salt. Okay, so when you they defined the piezoelectric effect like this: when the piezoelectric crystal is subjected to the external pressure, the field is developed on opposite faces of the crystal. This is also known as the piezoelectric effect. The converse of this effect is also observed to be is found to be true. Means so instead of applying pressure, when the piezoelectric crystal is subjected to the external electric field, the change in dimension of the crystal takes place. Okay, so the change in dimension of the piezoelectric crystal under the influence of external electric field is also called inverse piezoelectric effect. From practical point of view, the inverse piezoelectric effect is very useful compared to the direct piezoelectric effect. Especially the inverse piezoelectric effect is used to produce the ultrasonic waves. Okay, so this is about the piezoelectric materials. Okay, the ferroelectric materials are also a class of piezoelectric materials. A piezoelectric material which are having the unique polar axis as well as which are exhibiting this hysteresis and spontaneous polarization behavior is also called ferroelectric materials. These are very important class of the piezoelectrics as well as dielectric materials. Okay, so because these are mainly used to store the electric charge. Okay, so the important group of the the dielectric materials. Okay, so this ferroelectric materials contains spontaneous polarization, means even in the absence of external field, they exhibit the polarization, but in the absence of the field the net polarization is 0. Okay, so we can understand this concept by comparing this with ferromagnetic materials. Okay, you know, the ferromagnetic materials also exhibit the spontaneous magnetization behavior. Okay, so even in the absence of external field, they consist some internal magnetic moment. Similarly, here also there is internal polarization or internal dipole moment even in the absence of the field. Okay, so we will compare this with domain theory. Okay, so the ferroelectric material is divided into n number of small regions. Each and every region is also called domain. Each domain acts as a dipole even in the absence of external field. But when you take the entire material on the whole, it consists n number of domains, and those n domains are oriented in n possible directions in the absence of external field. That is the reason why the net polarization or net dipole moment is equals to 0. But when you take individual domain, okay, that consists permanent dipole moment. In case of ferroelectric materials, the domains are needle shaped, and diameter of each domain is of the order of 10 to the power of minus 6 meters. Okay, this is the reported values. Okay, right. So this ferroelectricity or ferroelectric phenomenon was first observed in Rochelle salt that exhibit this ferroelectric behavior in between this 18 to 22 degrees centigrade. Okay, so ferroelectric behavior means that exhibits the property of spontaneous polarization in between these two temperatures. Okay, spontaneous polarization behavior. Okay, right. Now, what are the special features of these ferroelectric materials? Okay, so the ferroelectric materials is mainly used in charge storage purpose. Okay, so here in case of ferroelectric materials, the value of dielectric constant or relative permittivity is very large when compared to all other materials. Okay, so the value ranges from 10,000 to 1,000 to greater than 10,000. Okay, because of this huge dielectric constant or relative permittivity, so they are suitable for charge storage devices. And this relative permittivity is not constant, it varies with respect to the temperature. Okay, so it follows Curie-Weiss law, T plus R minus Tc. Okay, so here when you increase the temperature epsilon r and T, when you increase the temperature, the dielectric constant also increases. At a particular value of dielectric constant, it suddenly decreases. Okay, so at this particular temperature, it suddenly starts decreasing. The relative permittivity value is suddenly starts decreasing. Okay, so up to this temperature it exhibits this ferroelectric behavior. At this particular temperature it changes from this ferroelectric state to the paraelectric state. So the temperature at which the material changes from this ferroelectric state to paraelectric state is also called Curie temperature. Is also called Curie temperature. Okay, so if you observe this, the spontaneous polarization. Okay, so what happens to the spontaneous polarization at this particular temperature? The existence of spontaneous polarization is nothing but ferroelectricity. Here at this particular temperature, the material changing from this ferroelectric state to paraelectric state. That means the spontaneous polarization gets vanished at this Curie temperature. Okay, so up to Curie temperature the material exhibits this spontaneous polarization behavior. After that the spontaneous polarization is equals to 0. So at Curie temperature the spontaneous polarization becomes 0 or it gets vanished. That is the reason why the material changes from this ferroelectric state to paraelectric state. Okay, at this Curie temperature. And one more important property that is exhibited by this ferroelectric materials is hysteresis. Okay, so when you increase the field, what happens? The polarization of the material also increases. Okay, at a particular value it reaches to saturation, and when you decrease the field after reaching the saturation, when you decrease the value of applied electric field, it doesn't follow the same path. It follows a path like this and it reaches this value. This is also called remanent polarization. Okay, when you still apply the field in reverse direction, it reaches here. This is also called coercivity, okay, or coercive force. And if you still apply the field in reverse direction, it reaches to reverse saturation point. Okay, after reaching the reverse saturation point, if you apply the field further in forward direction, it completes the curve like this. So this irreversible curve that obtained by drawing a graph between E and P is also called hysteresis curve in ferroelectric materials. So you can compare this with ferromagnetic hysteresis. Okay, so this is also called remanent polarization, and this one coercive force. So this is one more the special feature that is exhibited by this ferroelectric materials. So because of these special features, these ferroelectric materials are widely used in charge storage devices. Okay, so these are also used in the temperature sensors and transducers. Okay, so these are also used in infrared detectors. So these are all the applications of these ferroelectric materials. Remember the ferroelectric materials are class of piezoelectric materials.